Before that, he was an assistant professor in the Department of Mechanical and Materials Engineering at the University of Nebraska-Lincoln and an instructor of medicine at Harvard Medical School. He received his bachelor's from Shiraz University and his master's from Sharif University of Technology in Mechanical Engineering. He later received his PhD from Simon Fraser University in 2011. He did 1 year postdoctoral fellowship in biomedical engineering at McGill and 3 years of postdoctoral fellowship at Harvard Medical School and MIT. His research involves design, fabrication, characterization of microsystems and fibrous materials for emerging engineering applications such as tissue engineering, regenerative medicine, and wearable devices. He has authored more than 180 journal papers, 5 book chapters, and have 14 patents. He's also delivered 90 seminars at various conferences and academic institutions. He has been cited more than 14,000 times and has been the recipient of many awards, including Answer Postdoctoral Fellowship, BCIC Scholar Award, Ali Nasser Prize of ISME. Floor is yours, Professor Tamayol.
Thank you so much for your kind introduction. So can you see my, let me go to full screen. You can see it?
Yes.
Thank you so much. So excellent. So today I'm going to talk about some of our translational research, which involves biomaterials and engineering technologies for treatment of skin and musculoskeletal injuries. And I'm going to start with the musculoskeletal part. But the majority of emphasis is going to be on the skeletal muscle. I'm going to just talk about some of our activities in the area of bone, treatment of bone defects. So skeletal muscles and bone defects are frequent. It can be caused by traumatic events, can be caused by blast injuries, tumors, or sometimes chronic diseases. But just to give you, an overview about the prevalence of the need, about 500,000 patients in the US are suffering from volumetric skeletal muscle loss, which they call it VML, and it involves, a removal of big chunk of the skeletal muscles, typically more than 20%. But there are other sources, types of muscle injury that typically are left untreated. So muscle and similarly bone, we are talking about 1 million cases of bone defects, which ends up requiring some sort of intervention, right, every year. But these two tissues are very excellent in terms of regeneration, but sometimes the extent of injury overwhelms the regenerative capacity of the tissues. And unfortunately, there's not much available in the clinic to address that, right? Then whenever you see something like this, that there is an unmet clinical need, that's where tissue engineers stand up and say that we are going to build you a brand new one, right? But when you think about muscle tissue engineering, you need to first think about the challenges that you have to overcome. You need to create an environment that supports cellular growth. Then obviously organization is key to the function of the tissue, right? So you need to create highly organized myotubes which are synchronized with each other. Then you need to think about mechanical properties, the biomimetic mechanical properties that you have to be able to achieve for the tissue to function. Then connection to the host body and host tissue requires proper innervation, vascularization. But one of the things that occasionally is disregarded is how to implant, even if you can fabricate, how to implant it properly. And so it's going to be functioning long term, right? But when you think about or you look at the injuries that we are talking about, a piece of muscle is gone, right? This is a mouse model of VML that we've worked on. So when you basically go into one of the muscles, in this case is GA, you take a chunk of that out, and then you leave it to see what's going to happen, right? So then, as you see here, this is after 8 weeks of injury, and you see that, the sham injury, which the muscle is intact. That's how it should look. And then after VML no treatment, you see that there is a deficit in terms of the muscle volume, and the same way it's that there's a deficit in the function, right? But what's happening, post injury typically is that it leads the tissue cannot regenerate itself. Instead, it leads to fibrosis and then permanent loss of function. And part of it is due to lack of mobility of satellite cells or cells that are responsible for regeneration. And those cells cannot generate extracellular metrics to compensate the volume that is gone. So then overall, there's not going to be much of regeneration. But then underlying conditions include deficit of some of important factors and, biological cues that are needed for regeneration. For example, what we notice, IGF-1, which is an important myogenic factor that can help with the maintenance of the cells, is being quickly diminished after volumetric muscle loss. And overall, when you combine all these together, lack of mobility of the cells, downregulation of important factors, and lack of presence of extracellular metrics, so you're not going to get much of regeneration. So people have started thinking about strategies that can fix this problem, including, as I mentioned, tissue engineers that try to build a piece of muscle in vitro and then do the implantation, or some groups that are trying to do combination. But we try to go very, very basic and try to go with the bare minimum that's going to give us some functional recovery. So one of the things that we noticed early on was the challenge of implantation. We fabricated different constructs using different technologies, ranging from textile, bioprinting, etc. But one of the challenges that we always faced was how to implant them and fix them in place, right? Because hydrogels are not suturable. So we decided to make things simple. We know that Gelma is adhesive if it's cross-linked directly on top of the tissue, remnant tissue. So we tried to get benefited from that. So we built basically inks of Gelma, sometimes carrying nanoparticles or growth factors, and then we use something that we call it pen printer, which is essentially like a pen. You directly write on top of the tissue and then deliver the material and cross-link them in situ. And then the in situ cross-linking basically leads to some sort of adhesion and traction between the material and the tissue, which avoids the dislocation without the need for suturing. So then this technology, we show that it's very easy to use. Surgeons can easily apply it for treatment of different types of defects. They can shape it in a way that they like it. And obviously, it can be used for carrying growth factors. It can be used for carrying cells. And as you see, the cell survival through the process is very good. And typically, cells follow the organization of the fibers and can form organized myotubes. And this is another example that we did. Basically, we shaped a piece of muscle. And one of our collaborators, who's a plastic surgeon, went and tried to reconstruct that, and he relatively precisely rebuilt the tissue. But one of the early experiments that we did with Gelma, we tried to incorporate VEGF into Gelma. And our thought was that VEGF is an angiogenic factor, so each time that you want a process to happen, angiogenesis and vascularization is one of the first things that should happen to support cells that are growing into the tissue, and later on, formation of functional survival and formation of functional tissues. And one of the things that we did, we kept the animals for 4 weeks. We ran them on treadmill, and what we noticed was that the maximum running speed of the animals treated with Gelma scaffolds carrying VEGF was not statistically significant from the sham injury, which is just skin is open, muscle is intact, right? But then obviously the maximum running distance was lower, but still significantly higher than VML injury not treated or VML injury treated with just Gelma. But when we looked into histology of the tissue, we noticed that there is not much tissue regeneration here. Although there was less fibrosis, but there wasn't any significant tissue regeneration. But when we looked into the remnant muscle, we noticed that we are seeing some hypertrophy, which means that the basic remnant tissue or the myofibers in the remnant tissue were getting stronger and larger, right? But then we start asking ourselves the question, why we are not seeing a regeneration? Gelma is a very good material. It's gelatin-based. It's a denatured form of collagen type 1. And if you culture cells in Gelma, it's going to grow, it's going to produce muscle-like structures. Why we are not seeing this in vivo? Then our hypothesis was that maybe it's because of the porosity or the pore sizes of Gelma, right? The pore sizes are about a few micrometers in Gelma, which is much smaller than the size of the cells. Now you have to think about, as I mentioned, cells do not like to, are not significantly mobile, right? They don't like to migrate. So you're adding a scaffold, which if they want to move into that, they have to denature it, they have to degrade it, and they have to restructure it, right? And then growth factors are not very available in the environment. So probably you're not going to see much of regeneration. So then our hypothesis was that if we can generate pores, large pores into this construct, then maybe we are going to see better tissue regeneration. So following this thought, we looked into the ways that we can generate porosity in gel. And one of the strategies that came to our mind was looking at, the way people make whipped cream or making, egg white or whipping egg white. And following the same strategy, agitating gel, we noticed that we can generate foam-like or colloidal structures, which are very stable. And the pore sizes in these scaffolds are fairly larger than size of the cells. But then when you look into the architecture of these scaffolds, you see multi-scale porosity, right? We do have larger pores that you can generate by printing, and medium-sized pores that are generated by the bubbles that are formed or encapsulated through the process. And then you do have the nano or micropores of gel, which are inherent to gel, right? So then when you combine this together, you are generating a hierarchy of basically porosity or pore sizes into the scaffold. This is a very interesting material. You can easily handle it. It's much easier than gelatin or gel to print. And it generates a lot of opportunities because the mixing is much limited than liquid inks, etc. So then it's compatible with stationary printers, stationary bioprinters, as well as the handheld device that we have. So then we could basically generate very, very complex structures in this technology. Then we went to our animal model and tried to basically see if this hypothesis is correct. So we tested 4 groups. One was the sham injury, which was only skin opened and no injury to the muscle, and then everything was sutured back. Then we had the VML injury, which was, skin was opened, a chunk of about 20 to 30% of the muscle was removed, and then basically the skin was sutured back. And then we had VML injury, which this time was treated with foam, and then we had another group which was treated with the foam carrying IGF-1. So in this particular case, after 8 weeks, what we saw was that obviously in the VML untreated groups, we see a deficit in the muscle, right? But then in both groups that are treated with foam, or the other 2 groups that are treated with foam and foam IGF-1, we see basically the muscle is more or less reconstituted, right? And you don't see significant deficit in the overall geometry of the muscle. And then when we looked into we performed functional testing, we noticed that there's a significant function gain in the animals treated with foam, as well as in animals treated with foam IGF-1. And this was more pronounced in the group that carried IGF-1. But then we started looking into the histology. First, we looked into, basically performed subcutaneous implantation in rats. So basically we opened the pocket under the skin of the rats, we printed in situ, closed it. And we also, the same way we printed gel mod, non-porous or non-microporous gel mod, which is the ink, non-foam gel mod into that pocket. And then when we compare that after 7 days, you see that it's very hard to recognize that kind of the border between the tissue and the foam. And it shows that the foam encourages cell growth, and it's more or less, encouraging the integration of the scaffold. After 7 days, we are seeing blood vessels into the foam, and these blood vessels are actually carrying, or you can see RBCs in these blood vessels. On the other hand, when you look into gel mod, which is not foam, after 7 days, you don't see cells inside gel mod. And there is a big chunk of material which is not even properly integrated with the remnant tissue, and so it can easily be detached from the remnant tissue. And then when we looked into our volumetric muscle loss model, so we looked into a couple of basically markers. First, we performed basically Mason trichrome staining, and as expected, the volumetric muscle loss VML injury animals which were left untreated, they had significant fibrosis at the injury site. The animals that received foam and foam IGF-1, they had much less fibrosis at the injury site. And then we also noticed that the presence of the expression of basically CD31 staining, which was suggesting that we do have vascularization in the new tissue, and also we noticed the basically location in some of the stained tissues. We noticed the presence of nuclei, which was central in these myofibers. So it shows that these myofibers are recently developed and they are not matured yet. As myofibers mature, the nuclei is going to be located to the periphery of the myofiber. And then we also noticed the presence and expression of neuromuscular junction, which was suggesting that probably these pieces of this newly formed tissue is actually connected and integrated with the remnant tissue. And then, as I mentioned, this was aligned with our functional testing that we performed. But one of the other things that we were curious about was that is there any way that we can augment this? And when you look into clinical practice, typically after any surgery that they try to, basically perform an intervention, and I forgot to mention in some cases of volumetric muscle loss, they have to perform more than 10 different surgeries to be able to, provide patients with some sort of functional recovery, right? And each of these surgeries are very excessive, sometimes involve removing pieces of tissue from one part of the body, placing another part of the body, takes about 10 to 12 hours of surgical time, and not necessarily can be applicable to all the patients. So the patient should be in a very good health condition before the surgery. But then to augment those, usually they try to perform physical therapy, and we try to also follow that approach, try to see if applying physical therapy on the scaffolds that we are placing, or the scaffolds that we are placing are going to be supportive of exercise therapy, and if they're going to see any further functional gain, right? So we followed the regimented exercise therapy on these animals. So obviously the sham animals had some basically significant gain in the function because they were working out. So then obviously when you work out, your muscles are going to get stronger, you're going to get better function. But then when we looked into the animals that were injured and not treated, we didn't see significant improvement in terms of the function. But then in the animals that were treated, were injured and treated with the foam carrying IGF-1, we saw a significant increase. So this was suggesting that the scaffolds further supported exercise therapy, right? And obviously this wasn't an optimal exercise therapy, and down the road, if this exercise therapy could be optimized per treatment, so then most probably the functional recovery is going to be even more, right? But then, as I mentioned, not necessarily all the time you have a big chunk of remnant tissue that you can rely on for regeneration. Sometimes, more than 20% or 30% of the muscle is gone. So then in that case, you need to think about, adding biological materials or cells into the system, right? So people have looked into 3D, sorry for coughing, I'm still coughing after a cold. So people have looked into different strategies for bioprinting. And, extrusion-based bioprinting is one of the most common technologies that have been used for generating muscles because of the fibrillar architectures that it can generate. And it mimics the structures that I showed a few slides ago about, skeletal muscles, right? But then the resolution of these printers are typically not very high, right? The size of the filaments that you generate are typically larger than 200 or 300 micrometers, right? And then when you think about the organization of, cells following the organization architecture of the fibers, you need literally fibers smaller than 100 micrometers or distances less than 100 micrometers for cells to sense the architecture and follow that, right? So to be able to overcome this barrier, we came up with a strategy in a way that we decided to incorporate some sort of, basically topographical cues within the filament that we were generating. So I worked with one of our good colleagues in Montreal Tech, and we adopted their technology, and then we generated basically using chaotic mixing. We generated we controlled the mixing of two different materials. The green was a non-cell permissive material, and the red is a cell permissive material. And in that case, basically, we could generate compartments of the material, targeted material within the filament that was being printed. So then in that case, this basically this architecture of the filaments could be controlled or could be tailored by the number of the mixing units that we were incorporating in this system. And then the distance, the size, etc., could be tailored. And then what we noticed is that, this architecture is important and is actually affecting cellular function, like spreading, like even differentiation, etc. So, for example, after 1 day of, or I think it's 2 days of culture, we saw in the fibers that has these compartments, cells start elongating very quickly. On the other hand, cells inside the the fibers that did not have these compartments, they did not even elongate effectively, right? So in a follow-up paper, we studied basically incorporating sacrificial materials in these systems in a way that could serve like as kind of microvasculature inside these filaments. And that was a study that was led by our colleagues in Mexico. And in that one, we also noticed that the presence of these microcapillaries significantly improved cell survival. And right now we are working on technologies to control these the shape and architecture distribution of these compartments to better mimic the basically architecture of skeletal muscles. And then these technologies are very flexible, right? And you can put these nozzles on a 3D printer and bioprint constructors, large construct with that. Or you can generate the fibers and then assemble them using textile processes into architecture, three-dimensional architectures that you want, right? And then obviously these sorts of strategies could be easily be translated to newly or emerging applications of muscle tissue engineering, for example, cell culture or cellular agriculture, right? And that's one of the things one of the potentials of these sorts of technologies. But in terms when it gets to bone defects, the mechanical properties or the needed mechanical properties are different. So most of the times people use polymeric materials like polycaprolactam or PLA, right? These are types of materials that people use, right? So in one study, we designed a pen that could be used basically for basic in situ printing of hard polymers made of polycaprolactam carrying a hydroxyapatite. And this basically printer could be used by the surgeon, and then you could basically paint scaffolds or construct scaffolds in situ. And we noticed that there was significant or enough adhesion to keep the scaffold in place during the surgical time. So these scaffolds, we optimized them. We showed that basically we can adjust the concentration of hydroxyapatite up to 40% of hydroxyapatite concentration were printable, and these materials were supportive or were osteoconductive, and they were supportive of basically differentiation of stem cells into bone lineage. And we are now working on basically extending this study and testing this into an animal model of bone defects. But now I'm going to switch gear to skin injuries and chronic wounds, which is also another big problem in the US. 6.5 million Americans are suffering from chronic wounds and burns, and the estimated cost is exceeding $25 billion, right? So these are very common injuries. It could, happen by in aging population. It could be, basically caused by underlying conditions like diabetes. But when you think about it, you feel that this should be a solved problem, but still this is the leading cause for limb amputation in the world, right? When you look into the cascade of wound healing, so it's when after injury, you're going to have basically the stoppage of bleeding. Quickly, immune cells are going to get into the site, try to clean up the debris, try to, basically remove pathogens, and then they start triggering the process of proliferation, where basically a temporary extracellular matrix is deposited, cells start growing into that, vascularization happen. Later on, fibroblasts and keratinocytes get to the site and then start slowly remodeling, and then closure happens, right? But in some populations, as I mentioned, we don't have enough angiogenesis, we don't have quick enough angiogenesis and vascularization, so then the tissue gets to the point that's become hypoxic or extremely hypoxic, right? And then, some patients have level of chronic inflammation, and when you have an injury, it basically magnifies that. And then, the environment, the hypoxic environment rich with proteins is going to be very suitable for pathogens, and the pathogens can sometimes even hijack the immune system and trick the immune system to become very aggressive, which they call it hyperinflammation case. And then that could lead to, permanent deficiency in terms of regeneration. And then obviously infection, when you have infection in an environment that's supportive of that, that could be life-threatening, right? But when you look into the technologies that are out there, surprisingly, these are the state of the art that we see and are being used in the clinic, right? And this is, scaffolds that can sometimes carry some factors, or mostly not, sometimes antibacterial compounds. And then we do have negative pressure wound therapy system, which are on purely mechanical system, mechanically stimulating the wound, nothing beyond that, right? So one of the projects that I had the opportunity to work on that early on when I joined Ali's lab was based on the vision of why don't we try to make things personalized in wound care? And that's an important kind of vision in medicine, right? Right now, most of the practice in medicine is based on one treatment fitting the most, right? But then slowly people recognize the deficiency of this vision or view or a strategy, and start making things patient-specific or personalized, right? And then in wound care, obviously, is one of the areas that every single wound has its own signature. So obviously, this means that it requires its own treatment, right? Personalized treatment, right? And then, but the problem is that there is not enough information available to the clinicians and care providers to come up with a strategy or personalized strategy. So the vision was to generate smart bandages in a way that they are equipped with sensors, and then also at the same time equipped with drug delivery systems in a way that they can basically sense, and based on the sensing parameters, deliver therapeutics as needed. So the first version of the device that we put together was relatively simplified. We had a pH sensor, a temperature sensor that was sensing the temperature and pH of the environment. Then we had thermoresponsive drug carriers that would release their payload once they were being triggered. And then we looked based on the literature, we used pH as an indication of infection, and the drug that we used was antibiotics. So if there was infection and significant changes in the pH, then antibiotics would be released. And then the reason that we used thermoresponsive drug carriers was that basically temperature within the ranges that we were using were very safe. The skin temperature is lower than core body temperature, so then that generates opportunity for external stimulation. So these particles were fabricated using microfluidic microfluidic systems. We intentionally made them larger in a way that if we want to trigger them multiple times, so we could, they could keep some of the payload and be triggered multiple times. And as you see here, initially we put some fluorescent dye here just to visualize it, right? So then once the temperature was increased, you see that the particle, napalm-based particles were shrinking, and that they would release their payload into the environment. And, once we tested that, we noticed there was some, some level of control, but at the same time, some level of unwanted release. And then when we looked into the multiple, basically release, multiple stimulation to release multiple loads, there was not much consistency in the release. But overall, it was working okay, right? And then we packaged that into a very, conformal packaging. It was wearable, and then the drugs or the antibiotics that were loaded were potent. We showed that by zone of inhibition assay and later on by a CFU count assay. But then we did a couple in vitro experiments to verify the function of this system. For example, we cultured cells, contaminated the culture of cells, and then we looked into a positive control, which was antibiotic was added to the culture, and then we had negative control where the patch was only had a layer of alginate on top, no antibiotics or no drug carriers incorporated. And then we had another one which has, with the alginate was carrying particles that were loaded with antibiotics. And as you see, the middle group, which is technically a negative control, we didn't see the scratch assay was not healed. But then in the positive control and the test groups, the scratch assay was healed after 48 hours. But then we also did another in vitro experiments or in vitro test, which we generated a chamber which was being perfused by basically cell culture media at the pH of 7.4. And then we placed our device at the bottom of the chamber, we fixed it at the bottom of the chamber, and then inoculated bacteria in that chamber. And as time was passing, the pH was being reduced because the bacteria or pathogens were growing into the system. And then we basically set a triggering pH of 6.5, and as soon as the pH was hit into 6.5, it started triggering the heater. And then we had two groups. One was the control group, which there was no antibiotic, and there was the sample which had antibiotics loaded into the system. And as you see in the sample group, the pH started recovering. So pathogens were or bacteria were eradicated, and then because it was continuous perfusion, so then slowly the pH started recovering back to 7.4. But then it was one of the first studies in the field, which was obviously state of the art, but we noticed that there were some deficiencies in that, right? As I mentioned, the critical temperature for napalm was 32, so necessarily it wasn't the most kind of suitable critical temperature for this system. And then, as I mentioned, usually we need multiple drugs with multiple dosages of multiple drugs, and they should be independently released, etc. So it convinced us to design another system which enabled us to basically release different drugs with independent dosages, and basically also we tried to fix the issue of critical temperature. So what we did, we decided to generate a copolymer of napalm and PEGDA, and then in that case, the unwanted release was significantly reduced at room temperature. And then the release was a function of temperature, and the critical temperature was very close to 37. Another thing that we did in this system, we generated fibers in which every single fiber was coated by a conductive material, which was acting as a heater. And then that was surrounded by a layer of alginate, which was carrying thermoresponsive particles. And then these were assembled or were woven into a fabric, which was still wearable. And every single fiber in that fabric could be triggered independently. And for example, when we triggered two of the fibers, you see that only those two fibers are shining under IR imaging camera, right? And then the rest are intact. So then we tested, the antibacterial activity. We showed that the antibiotics are still potent after being triggered by temperature release, and both using a zone inhibition assay and also CFU count assay. But then we decided to see or to show the necessity of having multiple drugs being released. And in this particular case, we created an in vitro model, which was a 3D culture of endothelial cells, and then basically contaminated this culture. And then we had three groups. The first group, which is shown here by E, is basically there was no antibiotics and no VEGF added to the basically the fibers that were placed inside the culture. In F, we had only antibiotics loaded. In G, we had both VEGF and antibiotics loaded in the system. And when we looked into that, we noticed that obviously group E, after a while, all the cells start dying. It's a live data assay, so green shows live, dead cells appear in red. And then in F, because antibiotics were released, cells were surviving, but there was not significant vascularization because there was no VEGF, right? And then in G, we had both soap cells survive and we saw significant vascularization. But when we went to animal studies and performed animal studies, we saw some level of improvement in terms of granulation, etc. But it wasn't a real improvement, and we didn't know why. Because VEGF is a very potent material, potent factor. It's one of the earliest factors that body used for inducing vascularization, and we were wondering why it didn't work. Now we started asking a question from ourselves, right? But then another thing in the system is that I always say if the patient with this device walks out in a good day of Texas, all the drugs is going to be released at the same time, right? So we decided to basically make this system more reliable and also ask ourselves why we are not seeing significant improvement. Then the question, the hypothesis that we had, or the problem that we've thought about, was that the drugs, we're trying to send the drugs through a diffusion process from the top. So when you topically apply drug, the drug should diffuse into the tissue. But in most of these cases, the tissue is covered by a layer of necrotic tissue. Some of the cells at the basically close to the border of the tissue are not very active, and they are not regenerating significantly. And you are typically targeting cells below them, right? And then in most of these wounds, there is exudate, or the wounds are exuding. So there's a convective flow outward, and you're trying to overcome that with the diffusive process. So it's not, most probably it's not going to work, right? So then this gave us an idea, and we decided to build a system and we tried to overcome this barrier, physically, basically force the drugs to go and get into the tissue. And that's where we designed our second or our new version of bandage. And it was a device which was basically the drug was being pumped into the system, and then we had microneedles on the at the interface of the wound, which was penetrating and then delivering their payload into the basically the wound bed. And then initially we fabricated these needles using 3D printing, and if you use one of these fancy 3D printers, you can use multi-material printing, and then you can have basically rigid needles covered by a flexible backing, and then this is going to be very flexible. It's going to conform to any tissue or any curvature, and then it can penetrate. These needles are not going to break, and then you can retract them later on, right? And this was our device, and showed how precisely we can control and program basically drug dosing. And this was a fancy thing that our team developed, and then it could be remotely programmed in a way that the drug release rate could be already programmed from miles away, right? But then we started thinking about, okay, so let's see if this is actually going to work in vitro. And then we created an in vitro model, which was mimicking the necrotic tissue in a way that we had basically a mesh, which was covered by a layer of agarose. And then we put our drug on top of that, and then we inserted our needles into that basically agarose layer, and then pumped our drug into that. And we saw a significant difference in terms of the drug that was in the bottom chamber. we did some animal studies, which was very successful. I'm going to go back to that. But then we start asking another question. So if it's only penetration of the drug, can we think about other strategies? For example, liquid jet injectors that are sending the drug into deeper tissue. What is the difference, right? Is it better to use macroneedles, or is it better to use a system that's going to send the drug into deeper layer, right? And these are the different, basically drug distribution that we are talking about. The middle is the topical delivery. M&A delivery is very similar, but it's, kind of a little bit deeper. But when you think about the gradient is facing basically the highest concentration is at the interface, and as we go down, you have lower concentration. But when it gets a liquid jet injector, first of all, it's very deep. But then when you think about it, the gradient is actually reverse. The majority of the drug is inside, and the concentration at top is not as high as the interior, right? So then we start testing it in animals. So we did a relatively large number of animals study, and we compared different groups, all sorts of controls that we could think about. Negative controls, macroneedles just delivering vehicle, macroneedles delivering VEGF, same thing with liquid jet injector. And one of the things that we noticed among all these groups, only the group that was delivering VEGF through macroneedles was very successful. And in all these other groups, there was not much significant difference between basically negative control, which was no treatment, and even delivering VEGF topically or through liquid jet injector, right? And then this was further verified by our histological analysis, as well as IHC analysis for CD31 and vascularization. And we saw significantly higher vascularization in the groups that receive VEGF using macroneedles, right? So that was suggesting that, one of the important things in wound healing the paradigm has been what to be delivered, when to be delivered, right? Because we do have the cascade, and, people want to, deliver drugs at the right time, right? But what we showed here was technically not only all those things are important, but also the point of delivery and the method of delivery is very significant. It was very important, right? And then we did one study on pigs, and we basically use the same system for delivery of VEGF, basically via macroneedles and topically. And one of the things that we noticed was there was a significant difference in wound contraction. And later on, we went to perform histology, and we noticed that in immunohistochemistry analysis that the scarring and vascularization was also very different when in the animals that receive VEGF through macroneedles. And keep that in mind. In pig wound healing is kind of similar to human. We do have two mechanisms. One is contraction. The other one is regeneration, right? Contraction is more of a reparative mechanism, and regeneration is obviously the regenerative mechanism, right? So then you want to have more regeneration than basic contraction. So that was actually a very positive thing that we observed. And right now we are fabricating needles with different architectures. We fabricate needles with different loading, in a way that from different materials, hydrogels. We could control the spatial distribution of the therapeutics, and later on translate them into the tissue. So we have we are still actively working in this space. But the last thing that I want to talk about is, not necessarily all the wounds are superficial in the way that, one growth factor or some couple of growth factors can induce regeneration. Sometimes you're talking about very deep wounds, which requires something beyond just, growth factor. You need also extracellular metrics to be placed there, right? So in this particular case, we also try to test our, handheld printer to see if this is going to be also potent for wound healing, right? And we deposited gel, not foam. We recently have done another study with foam, and it was very potent, but I don't have it here. But it was just regular gel, and then regular gel carrying VEGF. And we created wounds on pigs, and we basically delivered the material using that. Looked into the the contraction versus regeneration. And we noticed that, in the animals that received the scaffolds, obviously contraction was less. But then you know, the overall wound size was also different, right? So then it showed that we had far more regeneration in animals that receiving Gelma with VEGF. But then when we looked into, you know, basically important things like the scar evaluation index, we noticed there was also far less scarring in the animal. But then when you look into the histology of these, basically the newly formed tissue, if you compare, you know, the new tissue that is generated with no, you know, after no treatment versus, you know, after treated with topical VEGF versus treated with Gelma and treated with Gelma carrying VEGF, you see a significant difference in at least the retinages here, right? And the more retinages, it means that the more mature is the tissue, right? And you see here completely different number of retinages and completely different pattern of the regeneration, right? So what we observed was that when we delivered the scaffold, which was carrying VEGF or growth factor, was actually significantly not only improving wound healing, but also improving the quality of wound healing. So that's something that we are continuing to you know, explore to see how far we can push this technology. So I would like to thank my team. You saw some of the pictures throughout the presentation. And this was, you know, one of our pictures back in Nebraska. This is a new one at UConn. I would also thank the, you know, basically funding agencies that supported our research throughout the past few years. Thank you so much. And if there is any question, I will be happy to answer.
Thank you for the fantastic talk, Professor Tamayol. A couple questions came in. One is, what was the tracer material you used for visualization of mixing in your experiments?
So in that particular case, we used basically fluorescent beads, very small fluorescent beads, so they're not diffusing out. So then that's what we used.
Thank you.
I'm assuming that they're talking about the chaotic mixing.
Thank you. Another question came in. In your opinion, is it more important to reduce the healing time of the wound or have a better quality of repaired or regenerated skin?
That's a very tough question, right? So you want to close it as soon as possible, right? Obviously, you want to protect the body, right? But one problem is that one thing that you want to be careful is that you're not closing it temporarily in a way that's going to rupture again, right? So that's the thing that you want to avoid. And in some cases, you want also to make sure that you are not inducing significant scarring, right? Because some of the wounds could be, in places that is important, right? If it's on the face, scarring could be, challenging down the road, right? So it's a combination, but keep that in mind. When you are designing your scaffold, you can design it in a way that it could prevent infection, etc., right? So then once you have a scaffold on top, the patient's still safe.
Thank you. You're delivering gels, biomaterials, and the person is asking, what do you think about probable side effects of your approach?
It's a tough question, right? What do you mean by side effects? If you
what happens to extra VEGF or after
that's actually, right, all right. So that's actually a good point, right? So usually when you're delivering your materials locally, right? So the amount of the scaffold that you're putting in is not significantly large, and the overall concentration of the factors that you have, if you want to dilute it over, if it gets to circulation, is not going to be much high to trigger process. But if it's too much, then that's something that you should be worried about, right? I agree, right? So it should be very carefully crafted.
Thank you. One person is asking, how do you deliver VEGF by transdermal injection?
So we use different systems. One of them was these microneedle patches that we fabricated, so you could patch on the animals and then you inject them. But there are also readily available microneedles that you can buy off eBay or Amazon and then do the injection. So all of them should work the same way.
Thank you. In slide 10, it shows that Gelma is a gel, wasn't integrated within the tissue. and there weren't any type of cells, fibroblasts, immune cells, etc. What do you think is the reason? Is it because of using a dense polymer network that hindered cell migration?
That's our assumption, right? And it's only day 7, right? 7 days is not a long time for materials or for cells to get into the materials, right? Especially when you're talking about germ, right? The concentration of germ that we use in this experiment was relatively high, right? Because we want to test the same concentration of the material that we are using for foaming. So then that could also be a factor. But overall, foams are more supportive of tissue ingrowth. Because it was also the same thing when we observed in our VML injury model, right? Because we used, in that one, gel model that we used was very soft. It was extremely soft, matching the properties of the tissue, still didn't have much ingrowth.
Thank you. How do you control the quantity of drug to be delivered? Is it gradient or specific dosage? And how do you decide on the VEGF concentration?
So there were different experiments, right? So in terms of the controlling for with the macro pump patch, so it was easy, right? We characterized the rate of the delivery of the pump. So then whenever we program the system, we knew that exactly this how much material is being delivered. And in terms of the concentration, we looked into the literature, and also we did some in vitro characterization to make sure that the concentration that we are targeting within the the approximate volume that we are targeting in the tissue is going to be basically clinically or biologically relevant. And that's how we ended up with the numbers that we have in the paper. If you're interested, I can send you the paper.
Thank you. Person is saying that what are the problems of these technologies for market or FDA approved?
So we talked about multiple different technologies, right? But for example, I'm going to give you the muscle one, right? So it depends on where, how you are framing it, right? For example, if it's only gel, there's no biologic involved. It could be considered a device, but then because the application, there's no predicate, so then you have to think about the de novo process. So you have to show, all sorts of things in terms of biosafety, basically, large animal models, basically showing that the efficacy of the system and safety of the system. And then once it's there, then you can think about clinical trials, right? But if you start adding, drugs or biological materials like cells, etc., then it's going to complicate things. So then you're going to be going down other pathways, which are going to be more costly, more challenging, right? So that's why we started with the bare minimum that's going to give us something, right? That is going to facilitate the translation.
Thank you. As you know that during wound healing, there's scar formation. Are you looking into wound healing without scars?
That's actually a very good question, and we have an interest, right? We are looking into. We have a couple of studies almost wrapping up, which we looked into immunomodulatory factors in a way that we can modulate the immune response in a way that, because the cause for scarring is that the response of the body is dysregulated, right? Body wants to protect itself. It throws whatever it has at it to make sure it's going to, close the opening as soon as it can, right? And that causes the scarring. So if you can regulate the process, modulate the process, hopefully you're going to have less scarring. And that's what we are hoping to achieve.
Thank you. One final question. What is the cross-linking mechanism of polynipam in the drug accommodation slide of 23?
We tried two strategies. One was photo cross-linking and one was chemical. But the data are with basically chemical cross-linking.
Thank you. Well, final question. Are you looking into anastomosis? You mentioned of the volumetric muscle loss. Are there strategies for anastomosis?
Well, I think that's one of the reasons that these surgical procedures that they use for flap surgery, right, functional flap surgery, are very time consuming, because the anastomosis is going to be very challenging, right? And usually they require multiple surgeons in the OR, and long processing time, right? So we designed some technologies that could potentially facilitate anastomosis, but at this stage we are not thinking about or looking into those functional flap transfers.
Thank you so much. So much interest in it. Thank you for the fantastic talk, and so much questions came in. Appreciate your time, Professor Tamayol.
Thank you so much for the invitation. It's kind of interesting to give a talk to your former lab, right? It's very exciting. Thank you so much. It was a privilege.
Thank you. Have a nice day.
Have a good one.